This meeting is being recorded.
Okay, Assalamu alaikum and very good morning to all my supervisor and examiners and to the viewers. So my name is Chapra Naz binti Muhammad Islam, and today I will be presenting with you my FYP topic, which is brain stroke classification based on deep convolutional neural network. And my supervisor is Dr. Chain. Okay, for the starting, we will go through the background studies, problem statement, research objective, and scopes, literature review that has been done in PSM1, methodology, design, and implementation of the experimental setup, result and the analysis, and then we will go to the deep discussion, and we will be packing up the work with conclusion and the future works. So moving on to the next, which is what is brain stroke? Why I have choose this topic? Okay, brain stroke is a serious public health problem worldwide, and many patients suffer from the brain stroke. Either it is a ischemic or a hemorrhagic brain stroke. So most probably patients above 30 or 40 start having these kind of problems, and once they even doesn't know what is happening. So for the ischemic stroke, it occurs when your blood flow to the brain is very slow and stop due to the blood clot when you have a high blood pressure. Patient may also experience stroke hemorrhage, which is like rupture of your nerves and resulting a serious complication. So for the doctor, it is very important to classify whether the patient has a brain stroke, tumor, or cancer in order to give the accurate treatment. So what is the research question? Okay, so first of all, which machine learning can be implied to improve the screening of brain medical images to make the classification findings by performing feature selections? And the next question will be how to implement the neural networks algorithm for stroke classification using MRI brain images to achieve the accuracy of validation or training. Then how to evaluate the finding using F1 matrix, recalls, specificity, and confusion matrix. So our first research objective is to study the available dataset and models for brain stroke classification based on MRI using deep machine learning techniques. Second is to construct neural networks models for classification of brain stroke subtypes. And lastly, to evaluate the performance based on the convolutional metrics, which is accuracy metrics, precision, recall, and F1 score. So our scope will be, we will be working with MRI images, which classified into hemorrhagic, ischemic, and normal brain from the patients. And the documented dataset used in this research will be only focused on a brain stroke subtypes or normal brain MRI images for the classification and prediction. And the programming language will be the Python. The measurement of performance based on the classification of accuracy and the algorithm efficiency. So this is the literature review that has been done during PSM1 using, so there are many diseases which uses DNN, ANN, CNN by UNet, and the machine learning and DL. And also LANET, SegNet, kernel spectred image, they have dataset, they have used MRI and CT scans, but there are many limitations which was found, such as large medical data set, which is from basically when you take any data set from the internet, it is not much accurate, especially when it comes to a medical MRI or CT scan images. And further studies will be aimed to detect and segment disease in a more precise and effective manner. So vascular enlargement and fine tuning in the disease area, because they have used CT scans. Most of the research uses CT scan because MRI dataset are not very available to a specific from the specific hospital or from a specific geographical background. So this is what we are going to do, what we are going to specialize from compared to a literature review to our current research frameworks. So over here we are going to do the pre-processing by grayscale conversion, normalization, resizing, labeling, and data augmentation, of course. Then further on, we will be feature extraction, where we will be label our images, region-based segmentation, and feature pixel features. And then we will perform the model architecture by using CNN, VGG16, and ResNet50. Then from the basic CNN, we will do the hyperparameter tuning. Then we will test from the trained system model and we will record the results. So first of all, to cover our RO1, which is to study the available data set that is available, we have done the literature review, problem identification, and data collection. To achieve our RO2 to construct neural networks, we have done data preparation, design algorithm, and the implementation of train network with CNN, VGG16, and ResNet. And then to cover our RO, which is last objective, research objective 3, to evaluate the performance of development CNN model with previous work in terms of accuracy, precision, recall, and F1 score. So we are going to do that after we already have our experiment set up and we already run the experiment and we already get the results. Then phase 4 will be documentation and thesis. So this is the first step where we prepare our data. So we have 20 patients. We have conducted our MRI from the Malaysian local hospital. So from there, we get 20 patients MRI data set, from where they are combinations of hemorrhagic, ischemic, and normal brain MRIs. So over here, we have done 2 setups. So for the experimental 1, we are going to use all the data set that we have, mix up with hemorrhagic, ischemic, and normal. For data set 2, we have done a special task where we separate the data set according to the brain imaging view. For example, we have separated into axial, sagittal, and coronal brain views to get more accurate, or to make our machine to learn more and to see whether the result is going to be same or not. So for the first experiment setup, resulting total number of 468 brain MRIs in experiment 1. For experiment 2, we chunk down the axial. Will go first for CNN, VGG, and ResNet. Then the second sagittal will go also for the VGG, CNN. So basically we have for each of sagittal, axial, coronal, we have 4 experiment, which is almost like gonna be 16 experiment gonna be done for dataset 2 and 4 experiment gonna be done for dataset 1. So okay, so this is the view how we are going to implement. This is the data set. This is the data set for dataset 1 for experiment 1, where we merge all the data set and we go once. And this is how we chunk up. Myself, I classified all the views according to the patients, labeled patients. So this is the axial view of the brain. This is the sagittal, which is the side part of the brain, and this is the coronal, which is the back of the brain. Performance metric, we are going to use confusion metrics. We have multi-classes where class 0, 1, and 2, which is hemorrhagic, ischemic, and normal. This is the measurement that we are going to use, F1 score, to evaluate the effectiveness and accuracy. We will be conducted validation accuracy. Sensitivity or recall represent how delicate the model predict. Then precision is measuring how precise the algorithm can detect the actual positive cases by calculating the true positive from the total number of true positive and false positive. So this is the formulation of our performance measurement. So for the experimental setup, as I have discussed before, I have given an overview. So this is importing of the libraries. We're going to use TensorFlow, Keras, NumPy, and ImageCog for image augmentation and others as needed. Then this is our first database, dataset 1. which we have ischemic, hemorrhagic, and normal. This is the load of directories. This is the second data set where we have axial, coronal, and sagittal. So both of the data set we have here we have 4 experiments to run. Here we have 16 experiments to run. First of all, we will go through data pre-processing, where we pre-process our image, then we augmentation, then we extract features, where we do the labeling, then we display the features, where we print out after and before, then we split the data set. Training set we have 60%, testing we have 20, and validation we have 20 as well. So this is how it goes. Here for experiment for merged, I call this merged brain subtype. So we have 1, 2, 3, 4, which is CNN, VGG16, ResNet, and hyperparameter tuning. And for axial, sagittal, coronal, we'll go one by one, like 1, 2, 3, 4, then sagittal 1, 2, 3, 4, then coronal 1, 2, 3, 4. Then after we have done we run our model architecture, then we will do the result analysis we will be having a test set and validation test, where we will be plotting accuracy plotted over epoch and loss plotted over epoch. We have 20 epoch to run for each of them. Then we will have a classification report and confusion matrix plotted. And then after getting all those result analysis, we will be doing the thesis writing and presenting as I'm doing now. So this is our first result analysis, where you can see this one is from the merge, from the experiment 1 using dataset 1, where it is like merge of all. We haven't separate any side views. So with heavier dataset, as you can see, ResNet gives a very good accuracy. So the experiment result for the merged brain, ResNet achieved the highest validation accuracy at 86.96%. Surpassing CNN and VGG, both of them have 83.7. But we do the hypertune CNN to get a good result, to see whether we can achieve more validation accuracy or not. So after doing that, yes, we have achieved a little bit more, which is 85% from 83.70%. So ResNet is likely to have a deeper neural architecture, which is better suited for handling the larger dataset, which is this dataset 1 is larger than dataset 2, which is already break down into chunks. So the best hyperparameter sets, we got 28 box, batch 16, activation ReLU. So this is the classes, hemorrhagic, ischemic, and normal. So here you can see what is the precision and everything. So analysis for the brain, for the merged brain subtype, as you can see, validation accuracy, the highest is ResNet, followed by the CNN with hyperparameter tuning, which is 16 batch ReLU, and then followed by the VGG and CNN basic. Okay, this is goes for the axial. So when we have done for the axial and sagittal and coronal, this is normal CNN, VGG, and ResNet 50. For all of them, it shows the highest accuracy of CNN. So CNN performs better in axial, sagittal, and coronal because reduction in the number of images for each class means subdividing into these imaging views. So likely led to a smaller data set. So traditional CNN may perform better with smaller data set because they are less complex and less prone to overfitting compared to deeper architecture like VGG16 and ResNet 50. So as you can see over here, we can conclude we can use CNN for a smaller data set, and my data set is basically from the local hospitals, so it does not have like, you know, that noises or that kind of image which is not clear. So it's very clear, all the images. So that's why CNN can perform well. We don't need having a complex neural networks to run on that. Then this is the result analysis for merged brain and also for the views. So as you can see, for the merged brain, we have 16 ReLU for the hyperparameter. Traditional CNN is 84%. it increased by 1%, 85. Axial, from using tradition like basic CNN, 88% accuracy, but when we use the hyperparameter with 32 ReLU, it got the validation accuracy of 92%. For sagittal, from 89 basic, it increased to 96% with batch 16, where we insert 16 images in a one flow, then ReLU, so it's 96%. Coronal, 32 ReLU, we got 93, which is also from 90 to 93 is also a increment of 3%. This is the confusion matrix for each of them, as you can see over the axial. So over here, axial shows 14, which is correctly classified as axial H is axial hemorrhagic, axial I is axial ischemic, and axial normal. And this is also H is hemorrhagic, ischemic, normal, hemorrhagic, ischemic, normal. So over here, 14 are classified correctly with axial H, 7 are classified correctly with axial I. One image was misclassified as axial I, as you can see here, axial I, and this one 0. We don't have any misclassified of axial N. For axial I, which is correct, axial I, which is correct, label at 7, 0 have misclassified. There is no misclassification of images. Axial N, also no misclassification of images. They have 14 images are classified as normal, which is correct. For sagittal H, 11 image were correctly classified as sagittal H, and there is none of them is classified as ischemic or normal, so which is also good. This one is also same, correctly classified 8, correctly classified no, there is none of them are misclassified. For coronal H, we have correctly classified is 9, but we have misclassified of coronal ischemic, which is 2, and there's none of them are misclassified as normal. And this one is good because there is 0, 0 for misclassified, but is correctly classified images. Number of images are 11. And this one is also correctly classified as 5. Misclassified is none. So next we move to the precision. This is for the axial imaging view. The classification report shows key metrics for model evaluation. Precision indicates the accuracy of the predicted classes with hemorrhagic and normal, both achieving 100% and axial ischemic at 88%. Recall, which measure the ability to capture the actual classes, is 95% for hemorrhagic and 100% for axial ischemic and normal. So the F1 score, balancing precision and recall, is 97% for hemorrhagic, and for ischemic is 90%, and for normal is 100%, which is quite good. Then goes for the sagittal. Sagittal also showing all instances of sagittal hemorrhagic, ischemic, and normal were classified correctly, which is 100, 100%, and the precision, everything is 100%, indicating no errors. The model has perfectly learned to distinguish between the different sagittal categories, as evidenced by confusion matrix and classification report, which I have shown just now. And for the coronal, over here, as you can see, for hemorrhagic and normal achieve 100%, but for ischemic is 85% due to some misclassification, as just now I've showed you. Recall measure the ratio of correctly predicted positive to all actual positive, and for hemorrhagic had a recall of 82%. Ischemic and normal is 100%. The F1 score for the F1 score precision recall was 90% for hemorrhagic, 92% for ischemic, and 100% for normal. For a conclusion, I can say the finding shows the ResNet 50 models perform the best overall using dataset 1, which is merged brain dataset, which include hemorrhagic, ischemic, and normal brain MRI from 20 patients of local hospital in Malaysia, with experiment 1 having the highest accuracy, specificity, and sensitivity or recall scores. So ResNet performs well with a larger number of data set because it is kind of complex. At the other hand side, scooping down into when we go to the chunks, like we already separate the images into axial, sagittal, and coronal brain MRI. The MRI performs well, the machine performs well with normal CNN compared to ResNet or VGG16. And for the next, okay, while VGG and ResNet 50, as I said just now, is architecture for image identification, the CNN model was chosen for this study due to smaller, because basically I focused more when we are like already classified axial, sagittal, and coronal. So the smaller dataset site, it doesn't need like very complex neural network or deeper architecture. So CNN, I choose CNN model to optimize with hyperparameter tune provide, and it also comes out with a good result where all the hyperparameter tune compared to the tradition basic CNN shows an accuracy even 2%. So making it more suitable for analyzing MRI images of the brain in axial, sagittal, and coronal views. The achievement is the study achieved its 3 primary objectives, where the first one is to study the available data set and models for a brain stroke classification based on MRI using deep machine learning techniques by constructing CNN models, where we have learned like basic CNN, tradition CNN, and we also did the hyperparameter tuning in CNN neural networks. Then we also played with the VGG16, ResNet 50 to see whether what is the accuracy level and how the neural networks perform. And then after we already done the experiment, we evaluate our performance in terms of validation and test accuracy, precision, recalls, and F1 score. Data was gathered from the previous resources and pre-processing steps like data augmented feature extractions were performed. And at the end of the experiment, the highest accuracy achieved were 96% for CNN and 86% for ResNet 50. So ResNet 50 in future can be used with a higher like larger data sets, and for CNN, smaller data set and a good data set. If you have a good quality of data set, you can go for normal CNN with hypertune. The future works can be done because in my research I have used 2D, which is two-dimensional image MRI, but further for good learning, in order to train our machine well, we can use 3D, which is 255 into 3, and then to improve the detection and diagnosis of neurological condition. Additionally, combining classification models with optimization strategy. For me, I use optimizer Adam. So maybe we can play there, we can optimize, and we can tune there the parameters, the neural networks in order to get a good result. Then of course, as just now I said, the activation and the learning rate. Then for the third, the performance of the model evaluation will be done according, Then after, when you are done with 3D, you already played with the hyperparameter tune, you can do the performance evaluation with accuracy, F1 score, specificity, and the classification of brain stroke subtype will be done with the highest accuracy obtained from the validation, because I choose also test accuracy and also validation to double confirm my accuracy, like how the learning rates work. So that's all from me. Thank you very much.